Before going into the architecture of Kubernetes, let's take a look at why Kubernetes came into existence. During the traditional deployment era, in which deployment used to happen on physical servers, there was no way to define boundaries with respect to the resources used by the applications on the physical servers. This caused resource allocation issues. So when multiple applications are deployed, there can be instances where one of the running applications take up most of the resources. One solution is to run each application in its own physical server, but this is not a practical solution because scaling applications would cause issues, and there's also issues with resource utilization. Also, physical servers cost money and therefore are not a valid solution for our problems. Then came virtualized deployment era. So in this, we used virtual machines. In this approach, we use multiple virtual machines or VMs on a physical server. This helps the applications to be isolated from each other, and the security is also improved as applications cannot freely access each other. Virtualization also helped in better resource utilization and scalability. While creating each VM, we can set the resources to be used by the VM. So there is now a way in which we specify the resources, the amount of resources which can be utilized by a particular application which is running inside the VM, right? But VMs are not a perfect solution either. Each virtual machine is just like a physical system where each VM has its own operating system, its own memory allocation. So we cannot keep adding VMs without causing a hit to the performance. And finally, let's talk about the container deployment era, in which containers are being used. Like this is the present generation. Containers are similar to VMs, but they share the operating system of the physical server. So each container can just have the application dependencies and run the application code. So containers are considered to be lightweight. Similar to virtual machines, containers have their own file systems, CPU, memory, process space, and rest of it. These are decoupled from the underlying infrastructure and can be ported across different clouds and OS distributions. Before going deeply into Kubernetes, let's look at some definitions which help us understand the architecture with more clarity. Let's look at the definition of containers.
The episode continues after this short message. If you like our work, please consider following us wherever you get your podcasts. Now, back to the episode.
Containers are application-centric methods to deliver high-performing, scalable applications on any infrastructure of your choice. Containers are best suited to deliver microservices by providing portable, isolated virtual environments for applications to run without interference from other applications. So, containers have the following advantages. 1. Agile application creation and deployment. When we use containers, it's easier and more efficient just to create a container image compared to the virtual machine image. Number 2, continuous deployment, integration, and development. Containers provide for reliable and frequent container image build and deployment with quick and easy rollbacks. Number 3, dev and ops separation of concerns. Create applications, container images at build or release time rather than deployment time, thereby decoupling the application from the infrastructure. Observability. Not only surface OS level information and metrics, but also application health and other signals can be observed. These are some of the advantages. But then again, when we talk about containers, it's also important to note that there are highly efficient and they can be densely packed. What I mean to say is the resource utilization is very good when we use containers. And also resource isolation is very good because when we run a particular application inside a container, only that application is running inside the container. There's nothing else running inside. So whatever we specify to be executed, or whatever needs to be running inside the container, only that will be running. Nothing else will be running inside the container. So if we need to access something else, so the container just needs to communicate with the outside world if it needs some other information. For example, we can have a container which runs all the processing, and we can have another container which just has the database. So these two can communicate with each other and perform the necessary tasks. The second definition that we'll be looking into is microservices. These are lightweight applications which can be written in various languages. In addition to the code, these also include the dependencies and the libraries and their environment requirements. So we write a particular application and we also specify the environment in which it runs and what dependencies and libraries are required for smooth execution of this application. So containers encapsulate these microservices and their dependencies, but they don't run them directly. Containers run container images. So let's talk about container images now. So a container image bundles the application along with its runtime and dependencies, and a container is deployed from the container image, offering an isolated executable environment for the application. So a container is built using the container image. So containers can be deployed from a specific image on many platforms, such as your the computer that may be in front of you, inside the virtual machines, or on public clouds. So now that we know about the definitions of containers and container image, let's talk about container orchestration. So container orchestrators are tools which group systems together to form clusters where containers deployment and management is automated. And it's automated at scale while meeting the requirements like fault tolerance, on-demand scalability, optimal resource usage, auto delivery to automatically discover and communicate with each other, accessibility from the outside world, seamless updates or rollbacks, and all this happens without any downtime. Few container orchestrator tools and services available today include the Amazon Elastic Container Service, the Azure Container Instances, the Azure Service Fabric, Kubernetes, Nomad, Docker Swarm, and Marathon, just to name a few. Most container orchestrators can group hosts together while creating a cluster, schedule containers to run on hosts in the cluster based on resource availability, enable containers in a cluster to communicate with each other regardless of the host they are deployed in the cluster. They bind containers and storage resources, group sets of similar containers and bind them to load balancing constructs to simplify access to containerized applications by creating a level of abstraction between the container and the user. They manage and optimize resource usage. They also allow for implementation of policies to secure access to applications running inside the containers. As Kubernetes is the container orchestrator that we are concentrating on, let's look at some of its features. The first one is automatic bin packing. So you provide Kubernetes with a cluster of nodes that it can use to run the containerized applications. You tell Kubernetes how much CPU and memory, that is RAM, each container needs, and Kubernetes can fit containers onto your nodes to make the best use of your resources. The second one is self-healing. Kubernetes automatically replaces and reschedules containers from failed nodes. It kills and restarts containers unresponsive to health checks and based on existing rules and policies. It also prevents traffic from being routed to unresponsive containers. The third feature is the horizontal scaling. Applications are scaled manually or automatically based on CPU or custom metrics utilization. Fourth, service discovery and load balancing. Containers receive their own IP address from Kubernetes, while it assigns a single DNS name to a set of containers to aid in load balancing requests across the containers of the set. Fifth, automatic rollbacks and rollouts. Seamlessly roll out and roll back application updates and configuration changes, constantly monitoring application's health to prevent any downtime. Next, secret and configuration management. Kubernetes manages secrets and configuration details for an application separately from the container image in order to avoid rebuild of respective image. Secrets consist of confidential information passed to the application without revealing the sensitive content to the stack configuration like on GitHub. Next is system orchestration. Kubernetes allows you to automatically mount a storage system of your choice, such as local storage, public cloud provider storage, or many more. The last one that we'll be looking into is batch execution. Kubernetes supports batch execution, long-running jobs, and replaces failed containers. And now, finally, we'll be discussing the Kubernetes architecture. The Kubernetes cluster consists of master and node. So, some of the components include the API server, the control manager, the etcd persistent storage, kubelet, kube-proxy, scheduler, and these components will be present on the respective nodes. Like some of them will be on the master and some of them will be on the node. Okay, first one, let's look at the control plane components. These make global decisions about the cluster, as well as detecting and responding to cluster events. Control plane components can be run on any machine, but generally setup scripts start all control plane components on the same machine, which is the master. Now let's look at the master. The master provides a running environment for the control plane, which is responsible for managing the state of the cluster and is behind all operations inside the cluster. The control plane components are agents with very distinct roles in the cluster's management. In order to communicate with the Kubernetes cluster, the user sends requests to the master node via CLI or the command line interface, a web user interface, or an application programming interface. It's important to keep the control plane running at all costs. Losing the control plane may introduce downtimes, causing service disruptions to clients with the possible loss of business. So the control plane is very important. To ensure that the control plane's fault tolerance, master node is not just one machine. So master node replicas are added to the cluster, configured in high availability mode. While only one of the master node actively manages the cluster, the control plane components stay in sync across all the master node replicas. This type of configuration adds resiliency to the cluster's control plane. Should the active master replica fail, the other replica will take its place and continue the operations of the Kubernetes cluster without any downtime. To make sure that the cluster state persists and its configuration data is saved, we use etcd. etcd is a distributed key value store which only holds cluster state related data, no client workload data. So it just stores the cluster state data and the workload of the client is not saved here. We generally configure etcd on the master node. It also can be configured on its dedicated host to reduce the chances of data store loss by decoupling it from the control plane agents. When stacked, high availability master node replicas ensure etcd resiliency as well. Unfortunately, that's not the case for external etcds. When the etcd hosts are configured in an external manner, that is, they are on their own dedicated hosts, we need to make sure that their replicas are created for high availability mode configuration. The master node has the following components. The first one is the API server. All the administrative tasks are coordinated by the kube-apiserver, a central control plane component running on the master node. The API server intercepts the calls from the user, operator, and external agents, then validates and processes them. During processing, the API server reads the Kubernetes cluster's current state from the etcd, and after a call's execution, the resulting state of the cluster is saved again into the distributed key value data store for persistence. The API server is the only master plane component to talk to etcd, both to read and to save the Kubernetes cluster state information, acting as the middleman for any other control plane agent requiring to access the cluster's data store. The API server is highly configurable and customizable. The next one is the scheduler. The role of kube scheduler is to assign new objects such as pods to the nodes. During the scheduling process, decisions are made based on the current cluster state and new object requirements. The scheduler obtains from etcd via the API server resource usage data for each working node in the cluster. The cluster also receives from the API server the new objects requirements, which are part of its configuration data. Requirements may include constraints that users and operators set, such as scheduling work on a node labeled with a particular label, with a particular key value pair. The scheduler also takes into account the quality of service requirements, data locality, affinity, taints, and toleration, etc. The scheduler is highly configurable and customizable as well. A scheduler is extremely important and quite complex in a multi-node cluster. Whereas in a single node cluster, the scheduler's job is quite simple because there's only one node and all the objects need to be scheduled on just that one node. Then comes the control managers. The control managers are control plane components on the master node, running controllers to regulate the state of the cluster. Controllers are watch loops, continuously running and comparing the cluster's desired state with its current state. In case of a mismatch, corrective action is taken in the cluster until the current state matches the desired state. The kube controller manager runs controllers responsible to act when nodes become unavailable to ensure pods count are as expected, to create endpoints, service accounts, and API access tokens. The cloud controller manager runs controllers responsible to interact with the underlying infrastructure of a cloud provider when nodes become unavailable, to manage storage volumes when provided by a cloud service, and to manage load balancing and routing. Then comes etcd. This is a distributed key value data store used to persist a cluster state. Okay, new data is written by appending to the existing data. Data is never replaced in the data store. Obsolete data is compacted periodically to minimize the size of the data store. That's it. It's not deleted. Out of all the control plane components, only the API server is able to communicate with the etcd. etcd's CLI management tool provides backup, snapshot, and restore capabilities, which comes in handy especially for a single etcd instance, which is common in development and learning environments. However, in stage and production environments, it's extremely important to replicate etcd in high availability mode for cluster configuration data resiliency. So when we talk about the stage and production environments, we generally make sure that there are multiple etcds available just to make sure that it's highly available. So these are the components inside the master node. Now let's talk about the worker node. Worker nodes provide running environment for client applications. Through containerized microservices, these applications are encapsulated in pods, which are controlled by the cluster control plane agents running on the master node. Pods are scheduled on worker nodes, where they find required compute, memory, and storage resources, and networking to talk to each other and the outside world. A pod is the smallest scheduling unit in Kubernetes. It's a logical collection of one or more containers scheduled together. To access the applications from the external world, we communicate with the worker and not with the master. A worker node has the following components. Container runtime. Although Kubernetes is described as a container orchestration engine, it does not have the capability to directly handle containers. In order to run and manage a container's lifecycle, Kubernetes requires a container runtime on the node where a pod and its containers are to be scheduled. These container runtimes include Docker, Containerd, RKT, and RKTlet. The second component of the worker node that we'll talk about is the kubelet. The kubelet is an agent running on each node, and it communicates with the control plane components from the master node. It receives pod definitions primarily from the API server and interacts with the container runtime to run containers associated with the pod. It also monitors the health of the pods running containers. Kubelet connects to container runtime using container runtime interface. Container runtimes used to be hard-coded in Kubernetes, but with development of CRI, Kubernetes is more flexible now, and it uses different container runtimes without the need to recompile. Any container runtime that implements CRI can be used by Kubernetes to manage pods, containers, and container images. The third component of the worker node is the kube-proxy. Kube-proxy is the network agent which runs on each node, responsible for dynamic updates and maintenance of all networking rules on the node. It abstracts the details of pod networking and forwards connection requests to the pods. These are the core components. Apart from these, we also need some add-ons. Add-ons are cluster features and functionalities not yet available in Kubernetes, therefore implemented through third-party tools and services. The first one is the DNS. Cluster DNS is a DNS server required to assign DNS records to objects and resources. Then there's dashboard. It's a web-based user interface for cluster management. And then there is monitoring and logging. So these 4 add-ons, we generally use third-party services to implement these features inside the cluster.
The episode will continue after this short message. If you like our work and would like to support us, you can visit buymeacoffee.com/Chintu. That is buymeacoffee.com/CHINTU. Now, back to the episode.